Advanced Dimensional Analysis, Problem Mapping. This video deals with solving long word problems, the kind you can't quickly see how to set up, the ones that might cause you to panic on an exam, that kind. There are secrets to finding a systematic approach through long problems that are not often explained in textbooks. That's what this video is about. Depending on what you've done so far, use it to develop new techniques or as a review. The problem used here will be one that involves no chemistry, although this technique is the major one used in general chemistry. It involves only multiplication and division, not addition or subtraction or algebra or formulas, although dimensional analysis could be used for parts of problems that require those operations. Before you work through this video, you should already be familiar with how to do simple problems by dimensional analysis, which, by the way, is sometimes instead called the factor label method. The general steps are outlined on this slide, a copy of which is available. The first three steps could be done in any order. We will focus here mostly on mapping the problem, which is step 4. It's a step that is often omitted in shorter problems where you can more easily see how to solve the problem. Here is the problem we will work on in this video. Pause the movie and read the question. Do you see how to do it right away? That's what I thought. To lessen brain freeze, we will first get rid of some of the clutter, like the whole first paragraph, which basically just tells us, this is an important question. Now, pause the movie, get out paper and pencil, and see what you think you should put for the first 3 items in our sequence of steps. Identify what is asked for, identify where to start the problem, and write all the conversion factors from the problem. Remember, all numbers should have unit and substance labels. Let's see how you did now. Identify the units of the desired answer. Where are we going to find that? In the question, marked by the question mark. The question is, how many kilometers? Units are kilometers. Identify where to start. It will be always the first number in your problem setup. Where do we find it? In the question usually. Not always, but usually. Here, it's how many kilometers would this automobile have to drive to consume 3.05 liters of methanol. There is a number and units. Our starting point is 3.05 liters of methanol. How are you doing so far? It sometimes is more difficult to determine where to start. It can help to read your what is asked for and where to start answers as a sentence and see if it makes sense, like how many kilometers from 3.05 liters methanol. That sounds like the question. If you can't figure out where to start, just go ahead and write all your conversion factors. It will sort itself out eventually. Now we'll write the conversion factors from the problem. You can check your work if you've already done this. First number in the problem that you see is 85%, so we'll put down 85 on our factor. 85% is 85 out of what? 100. So we put 85 on the top, 100 on the bottom, and this will represent percent. Now we need units. Percent can be by mass, by volume, by mass volume, or something else. We need to be told what type of percentage this is. Here, by mass. So our units will be mass units. We might as well use grams since grams are in other factors in this problem. The units are the same on the top and the bottom because it's 85 parts out of 100 parts. If it's by mass, they both have to be mass units. Now what's substance? It's 85% what? Methanol. So it's 85 grams methanol. And when you're talking percentage, it's always out of a mixture. It's methanol mixed with gasoline, and so you might think that the mixture is called gasoline, but no, the mixture is both methanol and gasoline together, which is called fuel. So our label on the bottom is fuel. You will do the same thing for the 15%. Notice that when you're doing percent by mass here, your units top and bottom will be the same, but the substances will be different. Now we'll move on to the next numbers in the problem. 25.5, 0.775, and so forth. Those will be part of factors too. 25.5 units on the top, miles, units on the bottom, gallons. Number on the bottom is 1. If it doesn't say how many gallons, it would be 1. The substance on the top, well, miles isn't a substance. The substance on the bottom, gallons of what? Is it gallons of gasoline or gallons of fuel? Fuel. Remember, gasoline is only a component of the fuel. The next three numbers are all densities. The units, grams per milliliter, which means 1. Now, 0.775 grams per milliliter is the density of what? Fuel. So it's grams of fuel and milliliters of fuel. Density is mass per unit volume of the same substance. This is different from the situation with percents because we have the same substance top and bottom and different units. Our other two densities are for the other substances, methanol and gasoline. And now for mapping the solution. I always do mapping first for long problems before attempting the setup. The idea here is to focus only on how we are going to get from the beginning to the end without any numbers. I don't want to sidetrack my brain with trying to remember some numerical conversion factors or picking up and putting down my calculator. You need to focus on the units, which is why it is so important to include those in your conversion factors. If there are no substance units, which is the first thing I consider, you look at the kind of unit. Here we have substance units for all the factors except for kilometers, which we'll look at the kind of unit first. I have highlighted the substance units. So our goal is to convert from methanol to kilometers. We will place the factors from the bottom up in the line of the map so that we have units only, not numbers. The top and bottom units of the conversion factor are laid out side by side with an arrow in between. The units will line up from left to right on the page with the factors having the same substance next to each other. You'll notice here I have the miles and kilometers next to each other because they're both distances. If the conversion factor is from the problem, I usually put a label above the arrow so I remember which factor was used. Here I have factor C, which is enabling me to convert fuel to miles so that I can then later convert miles to kilometers. We will use this information later in the setup as shown here. That would be our conversion factor. If we have gallons of fuel, you multiply through to get miles, and that will be part of your setup. But we're going to finish the layout of the map first. We had placed fuel to miles as a factor on our map in order to get from methanol to kilometers. But there was still a gap from methanol and fuel, so we need a conversion between methanol and fuel. If you look at the factors, you see that what we can use is factor A, which is the percentage of methanol in fuel. So we've lined that up now in our map so that the methanol terms are next to each other and the fuel terms are next to each other. We have completed mapping the solution in terms of substances. We have a way to get from methanol to fuel and from fuel to distance. But we still have gaps in our map, and for that we need to go to the kind of unit. In this slide, I have used the same factors but have highlighted the kind of unit. The volumes, liters, gallons, and milliliters, are all in purple. The masses, grams, are in blue, and the distances in yellow. To get from the first term in our map to 3.05 liters of methanol to grams of methanol, we're going from a volume to a mass. What converts volume to mass of the same substance? You got it. Density. We have a term for density. One of the factors, E, is the relationship between mass and volume. It's milliliters, so I'm going to put down milliliters on my map. You will notice we still have a gap between liters and milliliters, but we'll take care of that with our metric conversions. Next, as we go across the map, we see another gap between grams of fuel and gallons of fuel. Again, a mass to volume relationship for the same substance, which again would be density. That's factor D in our list of factors. We still have some other gaps, but all of the other gaps are simply metric English conversions. So let's move on to that factor. Now we'll go back through the map again from left to right. Liters to milliliters, we know that conversion. That's 1,000 milliliters to a liter. It's the same substance. Going across, we now have to get between milliliters of fuel to gallons of fuel. There are a couple of ways to do that. You can either go from milliliters to quarts of fuel and then quarts to gallons, or you can go milliliters of fuel to liters of fuel and then liters to gallons. It depends on what factors you know or are given in your problem. The last one would be miles to kilometers, which would either again be given to you or you might have to had memorized that one. So here we have completed the map, and now we'll go on to doing the solution setup for the problem. Now we will set up the solution. You notice here we have the map across the top of the page, the factors from the problem, and then the solution setup. The crosshatches on the solution setup are instead of the times sign for multiplying the factors. Notice in the factors list we are missing two factors, factor B and factor F. We didn't need those factors. They were extra in the problem. Is that fair? Of course. In many chemistry problems you have extra information, as well as in problems in life you have extra information, and sometimes you need to pull in information that wasn't mentioned in the problem. So let's do the setup, starting with the 3.05 liters of methanol. We place it on the top of our fraction in the bottom setup. We'll convert to milliliters of methanol. That's your conversion, metric conversion, 1,000 milliliters to a liter. Then we need to convert milliliters of methanol to grams. This is conversion E, which is our density. Because I mentioned that over the arrow, we have E. It's easy to find it. Then we go to the conversion between grams of methanol and grams of fuel, which is factor A, which we now put in. But we need to check our units. We have a problem here. In the setup, we do not have a cancellation between grams of methanol and grams of fuel. Those are different substances. We made a mistake putting in the factor in the way we did. We need to take it out. Now we'll put it in upside down. So we have the grams of methanol on the bottom of the factor to cancel grams of methanol on the top of the previous factor. This means that our solution so far is being divided by the 85% methanol, but we didn't have to figure that out because it is going to be determined by the units here. Our next factor will be grams to milliliter, factor D, the density. Notice you have to put the grams again on the bottom and then finish up with the rest of the density factor. Our next term will be milliliters to quarts, just a regular conversion factor. Quarts to gallons, which is 4 quarts to 1 gallon. Then the factor from gallons to miles from the problem, 25.5 miles per gallon, and then finishing up with just a conversion between miles and kilometers. Now all we have to do is to get out our calculators and multiply all of the numbers on the top of all of the factors together, and then divide by all of the numbers on the bottom of all of the factors. When we have finished that, we round off to 3 significant figures because that's how many the numbers in the problem had. And we come up with 39.5 kilometers. Uh-oh, overload. Well, we finished the problem anyway. I hope this helps.